Hello, so I created a problem revolving around the myth of Sisyphus, who's attempting to push a giant boulder up a hill. So, in this problem, Sisyphus is attempting to push a 2,000 kilogram boulder that reaches 12 meters tall up a frictionless 52-degree slope. So, the gods were merciful on him. There's no friction at play here. And it's a perfect sphere. At what minimum velocity does he have to push the boulder in order to overcome the force of gravity? So, I went ahead and I already drew our little diagram here. And so we've got Sisyphus pushing the rock up the hill, and there's a certain acceleration that he's going to reach if he overcomes the force of gravity. So we're going to go ahead and make a little force body diagram for this. So we have our F, that's not enough, F, B, D. We have our point right here. Since it's on a slope, the normal force is acting not wavy, but in this direction. And then our force of gravity is going to be going straight down. We also have, let me label those. That's the force of gravity. We also have our force of gravity in the y direction. Let me do a different color for that, which is equal and opposite to the normal force. We're not going to worry too much about that one, G and the y. And then we also have our force of gravity in the x direction, which is the one that we're going to be worrying about because it will help us determine what acceleration we have to do. So now we're going to start by doing our knowns, and we're going to figure out what exactly is unknown. So what do we need to calculate here? Forgive me, my screen is a little bit glitchy. I'm trying to screen record on an app I haven't before. So what are our knowns? So we can go back to the problem up here. The first thing that we know is we know the mass of the boulder is 2,000 kilograms. So mass equals 2,000 kilograms. We're not told the radius of the boulder in this problem that I made up. I don't know why I'm saying we. I don't tell you the radius of the boulder, except I do say that it is 12 meters tall. So from here to here is 12 meters. And the radius is going to equal 12 over 2, not radius, over 2, which is 6 meters. So we also know our theta, our angle of the slope, is 52 degrees. And one last thing that we know is the force of gravity is 9.8 meters per second squared. I prefer to keep it positive because we're going to be subtracting it since it's in the opposite direction of where we want to go. So our unknowns here, it's looking like we don't have a lot of knowns. So we're going to have to kind of backtrack and find some things first. So our main unknown is that we want to find the minimum velocity that he has to reach, right? So we want to find v. In order to find v, we have to find exactly what acceleration Sisyphus needs to be pushing the rock at. And since it's a sphere, we're going to have centripetal acceleration, that little c right there. And that'll come into play later. Lastly, we also need to calculate, we're going to actually do this first, we need to calculate the force of gravity on the boulder, and in turn, the force of gravity in the x direction, because again, that is the one that's going to be acting against our acceleration, right? So we're going to start by setting up that equation for the F sub g of the boulder, which equals mass times gravity. We're given the mass. The mass is 2,000 kilograms. So F sub g is equal to 2,000 times 9.8, which gets you to about 15, sorry, my bad, I skipped a little bit ahead, which gets you to about 19,600 newtons. So that's all great because we're going to know our force of gravity in this direction, but we want to know the force of gravity in this direction, which is the F sub g of x. And to find that, F sub g of x is equal to force of gravity times sine of theta. We could have also simply said that F sub g of x is equal to mass times gravity times sine of theta because these two are equal. I just wanted to do it a bit separately. So now we're going to plug in our values, and I'm going to change color just to separate. So to plug in our values for force of gravity, we have 19,600 newtons times sine of our theta, which was 52. And altogether, that gets us to about 15,445 newtons. And that is the force of gravity that is going to be pushing this rock downhill against Sisyphus. So we want to know, what's it going to take for him to overcome that? So what does Sisyphus's net force have to be? Or what does his actual force have to be in order for the net force to be greater than 0? Because that is what's going to get us to actually move in this direction, right? So the net force of this system, we know, is going to be equal to the force that Sisyphus is going to be putting on. So we'll call that F sub S minus, because it's acting against it, remember the force of gravity is going in this direction, minus the force of gravity in the x direction, right? So we can also say that this is F net in the x direction because we're not accounting for our y direction in this problem. And since F net has to be greater than 0, we can say that this too also has to be greater than 0. So now we set this back up as our inequality. F sub s minus f sub g of x has to be greater than 0. So we can add our f sub g to x to both sides as you do algebraically to solve this inequality. And you get f sub s has to be greater than f sub g of x. Cool, right? Well, what exactly is F sub s? The force that Sisyphus is exerting. Well, any force is going to be its mass times acceleration. And as we said earlier, Sisyphus is pushing a sphere. So it's going to have a centripetal acceleration here. So now we can plug this into this inequality for our F of s. So we get mass times centripetal acceleration has to be greater than F sub g of x. And the reason why we're saying greater than, not greater than or equal to, is because if it was equal to 0, then there would be no movement at all from either side. We want him to be able to move. So we can now plug in the values that we know, or actually we have to rearrange this equation first because we don't know the centripetal acceleration. So we have to solve for that. So we're going to divide by m on both sides, and we get centripetal acceleration has to be greater than f sub g of x over m. Now we can plug things in. So we have our centripetal acceleration is greater than our value we got here. So 15,445 newtons over our mass, which was our 2,000 kilograms. So this means that centripetal acceleration has to be greater than, let me check in my notes here, comes out to about 7.72 meters per second squared. But we want to find the velocity. So how do we do that? We're going to take our last equation, which is our equation for centripetal acceleration. So a sub c is equal to b squared over r. We don't really need to say the greater than at this point because we already got that in this problem. We just want to know that if the acceleration is at least this, what does the velocity have to be? So now we're going to go ahead and solve for our v. So we do that by multiplying both sides by r to get RAC equals b squared. Now we're going to cancel out that squared by finding the square root of each side. And your equation becomes v, oh, that's the marker. That's not what I want. Your equation becomes v is equal to the square root of RAC. And we know our values for r, and now we know our value for AC. So you can plug that into the equation, which is v equals the square root of 6, which is our radius, times 7.72 meters per second squared, you get about v equals the square root of 46.3, which comes out to about 6.8 meters per second. So Sisyphus has to be pushing with a velocity of at least 6.8 meters per second on his sphere to get it to move. Thank you.